Good morning, students. Welcome to Commutative Algebra lectures. In this lecture, we'll discuss about valuation rings. Okay, so let's start with definition of a valuation ring. So take B, which is an integral domain. Okay, and K is its field of fractions of B. Okay, then we say that this B is a valuation ring. B is said to be a valuation ring of K if you take any non-zero element. For any non-zero element x in K, either x should be in B or x inverse should be in B. Okay, so either x or inverse of that should be coming from B, then we say that B is a valuation ring. So you can quickly see that if you go to example, this Z is not a valuation ring, not a valuation ring of Q. Why? Because you can find n number of elements, suppose say 2 upon 3, which is a rational number, but neither 2 upon 3 or 3 upon 2, which is inverse of 2 by 3, are not in Z, right? So therefore Z is not a valuation ring. Okay, but we can construct a valuation ring. Here we can give, for example, take this, for every rational number you take out the maximum. P is any prime, so take out the maximum power of prime from that. So you can write, collect this, okay, where r is greater than or equal to 0 and p does not divide m as well as p does not divide n. If you collect this one, then this R will become, then this R is a valuation ring. So I'll simply write VR of Q. You can easily check that, because A by B, if A by B is there in Q, then it can be written in this form. From A you take out maximum power of P, and B you take out maximum power of P. Then that means there is no division, multiple of P in M as well as in N now, right? Then depending on whether R greater than or equal to S or R less than S, one of this A by B or B upon A will be there in R, right? That shows that this R is a valuation ring. Usually we will call it this as a pth valuation, which you will see later. Okay, fine. Oh. Now some of the properties we will see for valuation ring. So suppose if B is a valuation ring, so you take this B is a valuation ring of K, where K is its field of fractions. Then we can prove that then B is always a local ring, and if B prime contains B, then B prime is also a valuation ring, and B is integrally closed. Okay, so proof is not at all difficult. We can quickly go through it. What is meant by proving that B is a local ring? We want to show that there exists a unique. We want to show that there is a unique maximal ideal. Then B will become a local ring, right? So how we construct this maximal ideal is we'll consider the set M as set of all non-units of B. That means some x is in M means what? Either x is 0 or x inverse is not in B, because if x inverse is in B, then x will become a unit, because x times x inverse will become 1, right? Okay, then we will show that first of all, because it contains all non-units, okay, then obviously it will become the maximal ideal. So first it is enough if we show that M is an ideal, right? So our claim is M is an ideal. So what is meant by showing that is an ideal? Take an element from the ring B and an element X from the set M. We want to show that. So our claim is, okay, our claim is A times X is also in M, right? We see if one of them, if either A is 0 or X is 0, okay, then obviously A times X is 0, which is always there in this M, right? Okay, because we have considered 0 as well as other non-units, right? So assume that A is non-zero as well as X is non-zero, right? Then we can observe that we want to show that Ax is in M. uh, so suppose Ax, okay, is not in M, then what are the elements here in M? Either that should be 0 or it is not here, right? So because Ax is non-zero and it is not in M, what we can observe is that Ax inverse belongs to B, right? Because if it is not in B, then Ax should be in M, but Ax is not in M, so Ax inverse is in B, right? This shows that X inverse, which we can write as A into Ax whole inverse, okay, this belongs to B, right? But which is a contradiction. Why? Because this is a contradiction, as our X, we have assumed it is in M, right? Our X is in M, that means it cannot be a X inverse cannot be in B, right? But we got that here X inverse is in B. That contradiction arised because of this one. We have assumed that Ax, suppose Ax is not in M, so that means this cannot be true. So our claim is proved that whenever A is in B and X is in M, then Ax is in M. Now we prove the other property for an ideal. Suppose X and Y are in M with X non-zero and Y non-zero, because if one of them is 0, then it is already there, X plus Y is already there, right? So if X is non-zero and Y is non-zero, then XY inverse of course is non-zero, and which is in an element of K. By using the fact that B is a valuation ring, so XY inverse is either in B or its inverse, that is X inverse Y. It should be in B. Suppose assume that this is XY inverse is in B, then we can clearly write X plus Y as by taking Y outside. So this as X Y inverse plus 1 into Y, right? You can see that this is in M. Why this is in M? Because this XY inverse plus 1, this is in B, okay, and this is in M. So therefore just now what we have proved the property from this, it belongs to M, right? That shows that X plus Y is in M. That means M is an ideal. So this implies M is an ideal, right? So if M is an ideal, then, and it contains all non-units, and hence it has to be the unique maximal ideal, because if you take M prime is a maximal ideal satisfying this condition, then obviously it has to be here, because M contains all non-units, right? So therefore M has to be equal to M prime, right? That shows that it is the unique maximal ideal. That means our B is a local ring, right? And the second point is obvious, because B, whenever B prime contains B and B is a local ring, we know that either X is in B or X inverse is in B, right? That shows that X is in B prime or X inverse is in B prime. So therefore B prime is evaluation ring. What is third one? Third one, we want to show that this is actually integrally closed. That means if you take any non-zero element X in K, which is integral over B, then we want to show that this X is actually coming from B, okay? Because it is X is an integral over B, it satisfies this equation, right? And B is a valuation ring, so therefore either X is in B or X is inverse in B. But if X is in B, that is what we want to prove. If X inverse is in B, then you take out x power n minus 1 common from this here. So x power n minus 1, if we take out common, what we have here is this. Because of integral domain and x is non-zero, so x power n minus 1 is non-zero, we can send it to this here. So what we have here is this much is non-zero, this much is 0, so therefore x is minus a1 minus a2 x inverse and so on, right? This actually belongs to B, okay, because we have assumed that x inverse is in B, right? That means their powers are also in B, okay? So in any case, we prove that x is in B, therefore it is integrally closed, right? Okay. Now we'll try to remaining lecture in this, we'll try to construct if K is any field, okay, we'll show that there exists a valuation ring, okay, you can call it B of K. Okay, this is the aim of this remaining lecture. For that, how we construct, take K, which is a field, so K is any field, and omega is algebraically closed field, okay. Then consider this sigma, which is a pair A comma F, where A is a subring of K, where A is a subring of K and F is a map from a to this omega, which is a homomorphism. Okay, if we consider this, then we can define easily a relation for any a comma f, okay, and a prime comma f prime elements here. We can define this relation if and only if a is a subring of a prime, and f prime, when you restrict it to a, it should be f. So with this relation, you can check that it is a poset and it satisfies John's lemma. So therefore, this has a maximal element. That maximal element we will call it as b comma g. So our b comma g is a maximal element of this sigma. Okay, and we will show that this b comma g is, this b is nothing but our local ring with maximal ideal m, which is kernel of this map g. Okay, so if you consider this as above, then b is a local ring with its maximal ideal m, okay, which is kernel of g, right? And proof proof again is not so difficult, it's easy. uh, you see, G is a map from B to omega. This is a homomorphism, right? So therefore, G of B is actually a subring of this one, where this is a field, right? So this is a subring, but it is omega is a field. So therefore, it is an integral domain. Okay, this G of B will become integral domain, and by using that homomorphism, this theorem, B upon kernel of G is isomorphic to the image G of B, but because this is being integral domain, what you get here is that kernel of G, that you call it as M, is a prime ideal. So you get this is a prime ideal. Okay, now uh, this S, you consider this because it is a prime ideal, you consider, you take the multiplicatively closed set, which is B minus M, then you take S inverse B. We know it is a local ring with maximal ideal, unique maximal ideal M. Okay, we'll show that S inverse B is equal to B. That is the idea. Okay, so our idea is to show that S inverse B is equal to B, which we know already is that B is clearly contained in S inverse B. So we want to show that S inverse B is contained in B and so on. Okay, right. So what we can observe is that this G is a map from B to omega. So we can extend this G extends map G bar S inverse B to omega by simply G bar of, if you take any element B upon S, we can simply define this by G of B upon G of S. Okay, then you can make sure that G of S is non-zero because S is in this S, which is B minus M and so on. So this is a well-defined function, right? Okay, so because G bar extends this G and B is contained in S inverse of B, therefore what we can observe is that B comma G is less than or equal to S inverse of B G bar. But this is a maximal element, right? Which shows that this has to be equal to this, right? Because it is a member. Therefore, S inverse of B is B, and because it is a local ring, so you get that B is also a local ring with maximal ideal M, right? Fine. Now, before going to that main result, we will have this important lemma, which says that if X is a non-zero element of K, okay, and you consider this B of X, subring of K generated by X and B, and M of X, okay, M of X is an extension, this is an extension of M in B of X. Okay, that means what you have here is B to B of X we have, right? And we have M here, which is a maximal ideal. Then we are extending this ME, we are calling it as M of X. Okay, this is an extension of M in B of X. Then what we have here is either M of X is not equal to B of X, or Mx inverse is not equal to Bx inverse. One of them should be not equal. Both cannot be equal. The proof is obvious. Is again, suppose assume that both are equal. That means M of X is again full, B of X, Mx inverse is Bx inverse. Then we know that one belongs to B of X. Okay, similarly one belongs to Bx inverse. So we can find least M and least N. so that we can write one as linear combination of this and one as linear combination of this. So here our m and n are least, so m and n are least. Okay, that means what, we cannot write uh, this one as linear combination of less than m elements here. Okay, but uh, because m and n, so assume that suppose m is greater than or equal to n, then multiplying this one by x power n and simplifying, we get that 1 minus v naught x power n is this, and v naught is coming from m, and m is a maximal ideal, so therefore 1 minus v naught you will get as a unit. Okay, this is a unit. So 1 minus v naught is a unit, so you can multiply by its inverse and you bring it this side. So therefore x power n is this one, 1 minus v naught inverse, multiply and call it this as wi's. Okay, but what we have observed is that x power n is linear combination of these things. So therefore x power m can be written as x power m minus n times x power n. So you put it here. So x power m is this, right? Now you substitute in 19.1, which is here. So therefore, in place of this x power m, we can write un up to um, right? Which is in place of x power m, you substitute this. So if you finally, you can observe that after simplification, this linear combination is less than m. So this will be contradiction to the minimality of m. That contradiction arises because we have assumed that both are equal, so which is not possible. So at least one of them is not equal. Okay. Fine. Now we can go to our main result, which says that this b comma g be a maximal element of sigma, then b is actually valuation ring of the field k. Okay, so whatever we have started with field k, then this b is a valuation ring of that field k. Okay, again, how we will prove? So say that, say consider x which is non-zero. We want to show that either x is in b or x inverse is in b, right? Okay. So by this previous result, whatever we have proved, you take mx inverse, bx inverse. So one of them is not equal. Okay. So suppose assume that we will assume that m of x is not equal to b of x. The other proof is similar. You can, if you consider this, you will prove that x is in b. If you consider this case, mx inverse is not equal to bx inverse, we will show that x inverse is in b. That's all. Okay. Fine. So take this b of x, you denote by b prime, then this b prime and mx is a extension of m in b of x. Okay, that may not be maximal. So there exists a maximal ideal, you call it m prime containing this mx. So you have mx which is contained in maximal ideal m prime of b prime. Okay, right? So now you have this b and natural inclusion bx, which we have called it as b prime, right? Now here m prime, this is a maximal ideal in b prime, right? So therefore its contraction m prime c, which is nothing but m prime intersection b, this is also maximal ideal, right? But we know already in b there is a unique maximal ideal m, so therefore m prime intersection b should be equal to m, right? And that is this one. Okay, and not only this, because we have embedding this b to b prime. Okay, so therefore when you go modulo m and modulo m prime, you get this same embedding. Okay, this you can call it as k, because the field of fractions k is nothing but b modulo m, and this you call it as k prime. Okay, so we got a embedding k to k prime. And not only this, k prime is nothing but, you can observe that because b prime is b modulo b of x, so therefore this is nothing but k of x bar, where our x bar is actually x plus m prime. Okay, x plus m prime, right? Then you can check that this x bar is algebraic over k because it satisfies this trivial polynomial, right? Because x bar is algebraic over k, so and k prime is k of x bar, so therefore this is a finitely generated algebraic extension. Okay, finite algebraic extension of k from Galois theory, we know that. Okay, right? So therefore the homomorphism g from b to omega, which you can check that this induces an embedding g bar from its field of fractions, that is k to omega. How you can give g bar of, if you take k which is any x plus m, simply take this as g of x. Okay, right? Now because this omega is algebraically closed, this is algebraically closed and k prime is k of x bar, which is a finite extension. That means this g bar can be extended, okay? This can be extended to g bar prime, which is k bar of x bar, which is k prime, okay? K prime to omega. Again, a standard result in Galois theory, right? Right. Now consider this a map f prime from b prime, which is b of x, okay, to k prime, which is nothing but b prime by m prime. You can say, we know that this is a natural map, simply sending any element to that element plus m bar coset, right? So this is a natural homomorphism, and we have g bar prime. So you can consider a composition g bar prime composed with f prime, that you can call it as g prime. Okay, this is a map from where to where, b prime to omega, right? So we got a g, this is, you can check that it is a homomorphism. So we have a g prime maps from b prime to omega, and not only that, when you restrict g prime to b, what you can check is that you get g. Okay, so therefore we can see that this g prime and b prime, this is an element of this sigma. Okay, is an element of sigma, and not only that, because it is a bigger than g comma b is less than or equal to g prime comma b prime. But as this is a maximal element, what we can observe here is that this b should be equal to b prime, which is same as b of x, right? And hence x belongs to b, right? Therefore b is a valuation ring. B is a valuation ring of K, because we have started with X non-zero element from K, we proved that X is in B, right? Okay, we'll stop here and we'll see other things in next class.